So we're going to look at a few more examples of chain rule here. And so the first one I'm going to have us look at, we're going to utilize that Leibniz notation a little bit more. So suppose we have y equals cotangent of u, and u is equal to x cubed plus 2. And so this is similar to something you might see in your homework. Find y and then find dy dx. So if I think about what y is in this case, so my y here is equal to cotangent of u, and u is itself x cubed plus 2. So u is this x cubed plus 2. So that's what y would look like if we were going to write it. Most commonly, you'll probably be given functions written this way, just as their functions of x to start. Now, in finding dy dx, there's really kind of two different ways you could think about it. If you go back to Leibniz notation, dy dx is equal to dy du times du dx. And so first we would take the derivative of y with respect to u, which is what you see here. So derivative of cotangent of u would be negative cosecant squared u. And then I would multiply by the derivative of u with respect to x, which is what du dx says. And so derivative of u with respect to x would be 3x squared. Now, we wouldn't leave that in terms of both u and x, so we would replace again our u. So let's first write that as negative 3x squared, and then we would replace the u with what we know it's equal to here, of course, which is the x cubed plus 2. So that's a way to kind of think through with the Leibniz notation. That's one way to think through how to get to your dy dx with Leibniz notation. Truthfully, myself personally, and some people prefer even when they're given like this original, what I have, y equals cotan of x cubed plus 2, if they're given it that way. Some people like to break it apart and say, okay, my u is x cubed plus 2, and that means my outer function is y equals cotan of u. And some people like that approach. I probably won't use that as often. I'm probably more apt to just kind of take this y and sort of directly then just say, okay, well, that's going to then mean that my dy dx is just going to be derivative of the outside, negative cosecant squared, with my inside left alone. So with the u, the x squared plus 2 left alone, and then times the derivative of the inside. So I'm probably more apt to just approach these problems in this type of a notation, as opposed to using what you see right here. This is using that Leibniz notation. But obviously that's perfectly valid and fine, and good to see both. Good to see both. All right, let's get into some more examples then. So typically you're going to be given not a y as a function of u and u as a function of x. Typically you're just given, a function of x to get started here. So that's what we're going to do. So suppose that, and we're going to compare several different things here. So for part A, suppose that we have y equals cosine of 5x. So I want you to keep thinking about these various forms that we summarized last time. So for trig functions, when it's the inside function, you apply your derivative rule for the outer trig function with the inside left alone, and then times the f prime. So anytime your inside function is more than just a plain old x, that is when you are going to need to know to use your chain rule. All right, so let's just take our derivative here. I'll just call it y prime. So derivative of cosine of a function of x is going to be minus sine of that function of x, of that inside function. That was more than just a plain old x, so by chain rule times the derivative of the inside, so times that 5, And thus our final answer here looks like negative 5 sine of 5x. So there, our trig function is the outer function, and the inside function on this one was the 5x. All right, now let's look at y equals cosine to the fifth of x. Okay, so first of all, you need to always remember with your trig functions, if I say cosine to the fifth of x, that's really cosine of x being raised to the fifth power. So we need to know that. Now, what is my inside function? My inside function this time is the trig function, is the cosine. So in the last couple of examples here, let's go back and highlight, here's my inside function, 5x. In this example though, it's the whole cosine of x that is inside of the fifth power function. So my derivative, the derivative of the outside is going to be our 5 inside function left alone to the fourth power. So inside function left alone here is cosine of x. So that is your derivative of the outside, and then times the derivative of the inside, and derivative of cosine of x is minus sine of x. So our final result here is negative 5 sine of x cosine to the fourth of x. Very different, obviously, result there. So it's identifying, what you'll often hear me saying is what is the outermost structure here, and then kind of what's inside of that. So that's what we want to kind of be careful of. Okay, one last one in this little series. Let's look at what would be the cosine to the fifth of 5x. So now we have a combination of both part A and part B. So first of all, we have to recognize that this is really cosine of 5x being raised to the fifth. Now, we have the primary inside function, and so kind of the outermost structure we're working under is similar to the last example. I have an inside function raised to an outer power. So the derivative of the outside is going to be 5 inside function left alone to the fourth power. The inside function in this case is cosine of 5x. But guess what? That's what we did in part A, and that requires its own little chain rule. So this time, if I'm just taking the derivative of cosine of 5x, it has its own little inside function. So the derivative of cosine of a function is going to be minus sine of that function, and what's on the inside there is the 5x, and then times the derivative of its inside. So with all of these, we've been having this derivative of the outside, and then I kind of indicate, the big times here, the derivative of the inside. And I don't always write that out in words, but let's kind of look at this outermost structure on this one. So this represents, so this part right here, this is the outermost derivative of the outside, and then times, this is, again, the outermost structure that we're working under here. This is the derivative of the inside. So that's the biggest structure. But then within that structure, what we ended up with was its own little, this is its own little derivative of the outside, and then times the derivative of its inside. So here's an example where we have a chain rule within a chain rule. And this is what's going to happen as we start doing more and more. We're going to be combining rules. So it will be really important for us to always be thinking about kind of what is the outermost structure that I'm working under here. So my final answer might look like negative 25 sine of 5x times cosine to the fourth of 5x. So that would be how we might write that final answer. All right, so let's just look at maybe another example or so. So suppose we have function f of w. I'm always a little bit bad about using too many x's. And let's let that be e to the negative 3 over w. All right, well, one of our manifestations of a chain rule is going to be, this time, the outermost structure of our exponential is our exponential function. And what's inside of an exponential function is what's up in that exponent. So let's go ahead and take our derivative here. So this is going to tell me that our f prime of w, so f prime of w, derivative of the outside derivative of e to a function is e to that function. Then times the derivative of the inside. So I need, actually, let's rewrite that just a second here. So this is our e to the negative 3 over w. That's my inside function. And now I need to take that times the derivative of that inside. Well, we might want to think of this, so as we're kind of doing this work, we might want to think of negative 3 over w as being negative 3w to the negative first. So negative 3 over w is negative 3w to the negative first. And that might be, a little more helpful then when I'm taking its derivative. So bring down the negative 1, that's going to be 3, and then w to the negative 1 minus 1, so that would be to the negative seconds. So that's the derivative of the inside. So we can rewrite that in a variety of ways. You could leave it as just kind of as it is, like 3w to the negative seconds, e to the negative 3 over w. If you wanted to move those negative exponents into the denominator, you could, and make it 3 over w squared e to the 3 over w. I'd say either of those would be certainly just fine on those. All right, so we've seen all the different types of an inside function. Something inside of an outer power, that was one that we did last time. In terms of that denominator, we're going to do a lot more of those. We also saw that in 3 part B, inside function raised to an outer power in 3b. We've seen the trig function as the outer function in 3a, and we've seen the exponential function as the outer function. So what we're going to start to do is complicate things a little bit for ourselves, and now we're going to combine the chain rule with other rules. So actually, let's do that when we come back next time.